Today we are going to be continuing to look at exponential function context and data modeling. We're going to review and use our Euler's number, which we see right here. If you remember from a couple lessons ago, our Euler's number is the natural number, and it is E approximately 2.718, blah, 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 blah. Like pi, it continues on forever, and we have a button for it in our calculator. We found it a while ago. All right. It is often used as a base in exponential functions that model contextual scenarios. It is a growth constant, which we use in place of b, that represents continuous growth and decay. And that is the key word that we want to look for, is continuous. When we are told a situation is continuous, this is the formula we will use. Y equals P times E to the RT. I call it the PERT formula. P-E-R-T. In finance, for an example, we would use E to help represent an interest rate that is being compounded continuously. Compounding means how many times interest is being applied. So like if you take out a loan or you use a credit card and you borrow money, in the case of a credit card, your interest is applied once per month. That is how many times it is being compounded. That word compounding is how many times the interest is being applied. This will be part of it, yes. Okay? So, in the case of being compounded continuously, that means instead of interest being applied only once per month, it's being applied continuously. So every single second, millisecond, nanosecond, our interest is being applied continuously. Now, in this formula, we have some different variables. We have the variable P. P represents the initial amount, or in the terms of money, is the principal. It's the principal amount, the initial amount, the starting amount. Our R is going to be the continuous rate. R for rate, should make sense. And T for time. E, again, E is not a variable, E is a constant. That is our Euler's number, or our natural number. So let's go ahead and look at problem number 1 and see what we need to do. So the value of $100 investment is invested at an annual interest rate of 5%. That is compounded, there's the word I told you to look out for, continuously. Find the balance in the account after 6 years. So, since we are compounding continuously, that is our PERT formula. So we have Y equals P times E to the RT. So P again is the initial amount. What is our initial amount for this problem? $100. E again, E is the natural number, so we're not going to put anything in for that. What is our R though? What is our rate? It is at 5%, and you guys have already said it, but what is that as a decimal? All right, and then T is our time, our number of years. So what is our time for this one? 6 years. So all we have to do is we just take that information and we put it into our equation. So that's going to be Y equals P, we said was 100. So 100 times E, and that's our natural number, that's a constant, to the power of 0.05 times 6. So, using your calculator, what does that equal to? So, where do we find our E? Where's the places we find it? So we go 100, and in the TI we have it two places. One is above the natural log, so second natural log. Where's the other place? Above the division. Casio, I believe it's just above the natural log. So E, and what are we putting inside there? What was that again? 0.05 times 6. So you guys should have got 134.985. Okay, now we're talking about money here. So how many decimal places do we want with money? 2, right? Because cents. So that'd be 99 cents. So 134 and 99 cents. $134.99. Problem number 2 is another continuous, but they've already given us our equation. It says the number of bacteria B in a particular culture can be modeled by the exponential function b of t equals 17 times e to the 0.31 t. I'm actually going to stop you. What is our initial amount? 17, right? Because that's our p. What is the rate of growth? The 31%, 0.31, right? Because that is our r. It's p times e to the rt. Now, it says, what is the number of bacteria in the culture after 5 hours? You guys should be able to do that, right? We have our function, finding it after 5 hours. So all we need to do is plug in 5. So go ahead and find b of 5. All right, ladies and gentlemen, we should have an answer. What did you guys get? 80.095? All right, that sounds good to me. Now, since we're dealing with an actual thing, bacteria, we can just say that that's approximately 80 bacteria, right? All right, part B, we are going to find the average rate of change. Do you remember that, guys? What did we use to label that? AROC, right? So this is our AROC. What is the formula for AROC? Good job. Now let's go ahead in terms of what we have here. What is our F? What's our function? It's the B of t, right? So that would be capital B, B of, what is our lowercase b, the A and the B? What's the B for this one? Be 7, right? Remember our interval A to B, 1 to 7. So that would be 7. So B of 7 minus B of 1 over 7 minus 1. Use your calculator, figure out what that is. Now, I don't want approximated answers. I want accurate answers. So that means do not use rounded and numbers in your calculations. Use the different things that I've taught you. I showed you storing last week. I've shown you using function notation before. There's a lot of different ways you can do this to get accurate numbers. Please do not use rounded numbers in your answer. I want accurate numbers, please. All right, ladies and gentlemen, let's go ahead and look at this. Again, I said I want accurate numbers. There are several different ways we could go about this. One of which I'm showing right here. You can type it all in. That is the entire top, right? I plugged in 7, plugged in 1. Do not think you have to do things individually. You can do it all together. I go ahead and do all that and say, there's the top. What am I dividing it by? F of B minus F of A over B minus A. What am I dividing this by? By 6, right? So I just say, hey, I'm going to take that answer and I'm going to divide it by 6. And there's my accurate average rate of change. Without a lot of work. I didn't have to write down long decimals. I didn't have to do any of that. I didn't even have to store. Could I? Yeah, I could have found f of 7. I could have found f of 1, stored them as a and b, and subtracted and done all that. Another way I want to remind you about, one that we did previously. You can also, and I saw somebody doing this, you can put the equation into y1. And then, remember, we can do our alpha trace and use function notation. y1 of 7 minus y1 of 1. And then again, on the bottom, divide it by 6. Same answer, right? So use the skills that I have given you. Don't forget them. Use them. There are a lot of different ways we could go about and get what we want. All right, so our average rate of change, accurate to 3 decimal places, 20.952. So this is equal to 20.952. Now, let's see if you guys remember this. I don't have it here, but whenever I ask for average rate of change, whenever I say find AROC, I can also, if it's contextual, I can also ask, what does that mean in the context of the problem? Do you remember me asking that before? That was a sentence. We started with, on average, what would we say for this one? Let's say it out. On average, what? The bacteria, on average, the bacteria is it increasing or decreasing? Why? Because it's positive, right? We have a positive rate. So on average, the bacteria is increasing at a rate of 20.952. We had units. What would our units be for this one? Let's at least write that down. What's our units? Bacteria per hour in this one, per hour. So we'd say at a rate of 20.952 bacteria per hour. And how do we finish the context? Over the interval of, well, reverse that, 1 to 7, right? So whenever I ask average rate of change, I could also ask it in context. So we don't want to forget that sentence, okay? Part C, find the value of T when the number of bacteria in the culture is 1,000. Now, on this one, 1,000 is not a time. This is the number of bacteria. So this is asking when B of T equals 1,000. What is the function B of T? What did I give you up at the top? 17 times e to the t, and we want that to be equal to 1,000. Now, solving this requires logarithms, and as I mentioned previously, we haven't done that yet. So, as I've showed you previously, what do we want to use? What do you mean break apart? Doing more work than we need to. We have done this. I have showed you this. When we have an equation like this that we want to solve and we don't know how to do it by hand yet, or it's just one we don't want to do by hand, put it into y1 and y2, graph, and what are we going to calculate? The intersection. Do you remember that? All right. So, graph it, you are probably going to need to adjust your window because this goes all the way up to 1,000. So you need to make sure your Y max is going up to at least 1,000. I would say 1,100. Okay? So go ahead and start doing that. I'll give you a minute and then we'll see where we're at. All right, ladies and gentlemen. So I have graphed my equation and 1,000. My graph is here. I have to adjust things. Now I heard somebody say zoom out. You can. I don't really like the zoom out because it zooms out everything and sometimes it doesn't always work the best. So instead, I'm going to adjust my window. First off, I know I'm going to be in positives here. So I'm going to take off my negatives. I'm going to leave my X max at 10 for right now. Y min, I can have that as positive. And what did I say the Y max should be at least? It needs to be something greater than 1,000. Somebody last year was like, oh, 1,001. I guess technically, but it's not going to be very helpful. So let's go up a little bit higher so we can actually see things. 1,100, 1,200 would be fine, 1,500, even 2,000, right? Just something bigger so we can actually see what's going on. Now, I see my exponential, I see the 1,000, but do they connect? So what do I need to adjust some more? The X max. So I'm going to go ahead and say, hey, my X max, I'm going to put it at 20, see if that's good enough. Yep, it was. All right. So now they're connecting. Do we remember how to calculate the intersection? Where do we go, guys? Where is that? Second trace, Casio's. You're going to the G-solve, right? Second calc. Which one am I picking? 5, right? The intersection. So number 5. Casio's. Once you pick intersection, you should be done. It calculates it for you automatically. TIs, I'm going to bring myself over. First curve, blue, I just hit enter. Second curve, red, hit enter. Guess, I would bring it over to approximately where my intersection is, hit enter again. My Y value is 1,000, that should be correct. So how long does it take to have 1,000 bacteria? about 13 hours, right? A little bit more than 13 hours, 13.143 hours. Remember, 3 decimal places is what I want. So let's go ahead and put that in. So we should have T equals 13 point, whatever it was, 144? 144 hours. All right. Any questions? Okay, once you have that, go ahead and turn the page, please. And move on. All right, growth and decay and percentage rates. Yes. So we were just looking at our continuous growth or decay. Everything else that's not continuous, we're going to just be using our A times B to the X. Let's see if we remember. What does A stand for? What does A represent? The initial amount or initial value. What does the B represent? The growth factor or growth rate. Now, for our B, we will use either one of these. 1 minus R or 1 plus R, depending on if we have growth or decay. So let's go ahead and look at our first problem here. Zeller Industries bought a computer for $4,600. It is expected to depreciate at a steady rate of 20% a year. We want an exponential equation. So that is going to be y equals a times b to the x, or t. What is our a? That initial amount, right? 4,600. Our b, well, before we get to our b, we need to determine, is this growth or decay? What kind do we have? Y. How do we know? That word depreciate, that indicates decay. So which formula for b are we going to use? 1 minus r or 1 plus r? The 1 minus r. Well, what is that r value that we're going to use? What's the rate that we have in there? Not percent, the 20%. What is that as a decimal? 0.20, right? 0.2. So my b should be 1 minus 0.2. What is 1 minus 0.2? 0.8. So can I write an equation then? Let's try it out. Y equals what? 4,600 times 0.8 to the power of x or t or whatever variable you want to use. Sometimes on this one we would use t because we're dealing with time, but you can put x as well. That's fine. All right, there's our equation. All right, I want you to do part B and part C. Part B, what will be the value after 5 years? And part C, when will the computer be worth $500? All right, so go ahead and find each of those, please. All right, ladies and gentlemen, let's go ahead and check in on our answers. So for part B, again, we're plugging in 5. So that is going to 5 years. That's an input value. So that should be 4,600 times 0.8 to the 5. Did you guys get 1,507.33? There we go. So that is how much it will be worth after 5 years. All right, when will the computer be worth 500? So again, remember, that is an output value. That is the amount. So that is when we have 4,600 times 0.8 to the x equals 500. So we have to do y1, y2, graph, and intersection. All right. What did you guys get for time on that one? How many years will it be? I heard that 9.945. 9.945 years. So it will take almost 10 years, but after 10 years, it will be worth only $500 instead of the original amount of $4,600. And that's what happens with technology. All right, problem 4, I want you to do just part A. Your cousin Bob bought a house for $550,000. The house market is on the rise, as it has been for a long time. Value of house is expected to increase at a steady rate of 1.4% per year. Write an exponential equation that could represent this situation. So what would that equation be? Shouldn't take you very long. What would that be? Okay, what would be our A? What's our initial amount, guys? What's our R? What's the R, guys? 1 point. What is that as a decimal? 0 point. So what's our B? Are we doing 1 plus that or 1 minus that? Why 1 plus? It says on the rise, right? So 1 plus 0.014 should be 1.014. So what's our equation? Y equals? To the power of x, right? All right. Part B and Part C are the same. You find out after 3 years how long will it take. So we're going to go ahead and jump over to the next page, please. I have 5 minutes. This won't take us that long. All right, so there will be times that we will be asked to compare two growth rates, and we will need to place them in the same interval of the dependent variable. So in this case, the same interval of time. So meaning, if we look at this first one, we are told that a certain bacteria is growing at a rate of 1% per day. So we have 1% per day, and we want to know what is the equivalent weekly rate of growth. So what percent per week would that be? And no, unfortunately, it's not 7. That would make it nice, right? That'd be easy, but it's not. Okay? So what do we need to do to find that out? Now I have a question for you. Which one is a longer interval of time? Which one's bigger, day or week? Week. Week's bigger, right? So I am going from a small to a larger. So if we are going from a small interval of time to a bigger interval of time, what we are going to do is we are going to have whatever number compares them, that number, and we are going to multiply it to x. Now, what do I mean by that? Well, let's go ahead and look at this. So I have 1% per day. This is growing. That's what it says here. So that should be B equals 1 plus R, correct? B equals 1 plus R? We good with that? So my B in this one should be 1 plus 0.01. Are we good with that? So that'd be 1.01. So what we are going to do is we're going to take that B value. Now that is per day. So that is really, we would say, to the power of D, per day. But we are now going to say, we are going to take that, maybe not equals, but we're going to take that, and instead of days, we're going to make it into weeks. How many days are in a week? 7. So we say 7 times W for week, 7 per week. Now, using the properties from last week, we would then say that would be 1.01 to the 7th to the W. Do you remember that from last week? Using that property. So calculator time, what is 1.01 to the 7th? Should have it already. What is it, guys? 7 to 1, right? So there is our rate. But we have to adjust something real quick. So I'm going to take that rate. So the actual rate that I want for my week, I'm going to take that 1.0721. I'm going to subtract 1, which is 0.0721. What is that as a decimal? 0.0721. What is that as a decimal? Or not as a decimal, sorry. That is a decimal. What is that as a percentage? 7.21%. And that's my answer. So 1% per day is the same as 7.21% per week. Now, before we end, and we're almost there, that was small to big. What do you think I would do if I'm going big to small? It would be a division. So I would have to take my x and divide it by. So if I was going from weeks to days, that would be x divided by 7 instead of 7 times x. So if I wanted to do problem B here, I would say, hey, we are growing. So again, that is a B equals 1 plus R. We have a rate of 30%, and this is over the course of a year. So we want to know what is the equivalent monthly rate. So we have 30% per year, and I want to change that into some kind of percent per month. And so the difference between the last problem and this problem is that we are again going from big to small in this case. So starting out again, we have our B value. B would be 1 plus 0.3 or 1.3. So I would take that 1.3, and this time I am going from years to months. So for every month, that is 1/12 of a year. So I'm going to do my months divided by 12. So last one we did weeks times days. Now we're doing months divided by the year, like how many months are in a year, right? So we find that comparison, right? There are 12 months per year, and so for every month, that would be 1/12 of a year. So we're going to go ahead and do the same thing we did up there. So that'd be 1.3 to the 1/12th power to the m. So we're going to go ahead and get into our calculator and figure out what that would be. All right, so that was 1.3, so 1.3 to the 1/12th power, and we have 1.022. 1.022. So that is 1.022 for every month. Now again, if we want to find the rate, we're going to go ahead and do our 1.022 minus 1, and that gives us 0.022, which would be 2.2%. So 30% per year is equivalent to 2.2% per month. All right, so let's go ahead and look at part C. We have the nation's GDP is forecasted to grow at a rate of 2.5% per week over the next year. What is the equivalent annual rate? Now, annual will be per year. So this is the annual rate. And they give us this right here, which we need. There are 52 weeks in a year. So we are starting, we have 2.5% per week, and we are wanting to know how much percent is that per year. So we are going from small to big, so that's going to be our multiplying like we did in part A. So 2.5%, so our B would be 1 plus 0.025, which would be 1.025. So we're going to go ahead and take that 1.025 and we are going to raise it to the 52 times every year. So maybe Y for year. So we're going to go ahead and say, hey, that is 1.025 to the 52nd power for every year. Now, normally I would not want to use a Y there because Y is usually our output. I'm just using that to represent per year. Normally we would have X, T, M, something else to represent that. So we go ahead and use our calculators. Going back to our calculator, that was 1.025 raised to the 52nd power, giving us 3.6111. Lots of ones going on in there. So going back here, we have that is equivalent to 3.611 to the y, using that for year again, not usually doing that. To find my rate, I'm going to do the 3.611 minus 1. That gives me 2.611. What is that as a percentage? That would be equal, we move our decimal place twice, would be 261.1%. So 2.5% per week is equivalent to 261.1% per year. So let's go ahead and look at problem number 6 and finish that one out. So we have the population of certain bacteria can be modeled by the function f of d equals 300 times 2 to the d, where f of d represents the number of bacteria after d days. So we're using d up there for days. What does the 300 represent in this context? Well, as we have seen, that is in the form a times b to the x. A is always our initial value. So 300 is the initial, the initial amount of bacteria. How many bacteria are present after 7 days? After 7 days. So let's see. That would just be f of 7 equals 300 times 2 to the 7th. So 7 days, and we're in days. So that would be that. Let's go ahead and go to our calculator to calculate what that would be. Oh, wrong calculator. There we go. All right, 300 times 2 to the 7th power would be 38,400. 38,400. So that is equal to 38,400 bacteria. So there is that many bacteria after 7 days. All right, part C, it says rewrite the function such that the growth rate is presented as a weekly rate of growth, W, instead of a daily rate, D. So we're going to go ahead and do that. So weekly, so we're daily to weekly. So we have daily, going daily to weekly. That is going from small to large. Let's see, small to large. Small to large, again, is the timesing. So we're going to go ahead and take our f of d equal to 300 times 2 to the d. And again, we're going to change this to f of w, and that will be 300 times 2 to the, and how many days in a week? There are 7 days per week. So that is equal to 300 times 2 to the 7th to the w. So again, 2 to the 7th, real quick on our calculator, 2 to the 7th is equal to 128. So our equivalent function, but as a weekly rate of growth instead of a daily rate of growth, would be 300 times 128 to the w. So that would be per week instead of per day. All right. And that finishes out these problems. Thank you for watching and have a fantastic day.